Hey everyone, I'm just going through the rotational energy worksheet that we were finishing up on Friday. We got through most of it, but I'm just going to go through the rest of it to kind of make sure that you're on the right track. The main thing of this worksheet is looking at how is it that different objects with different moments of inertia affect how fast it's moving as it rolls down a ramp. So this top part we did in class together. We basically derived what kinetic energy for a rotating object is. Just remember, you do have linear kinetic energy, or like KL, which we decided here in class to call it, and that is our normal 1/2 mv squared. That is the energy of an object that's just kind of moving in a straight line. Now, if you have an object that is rotating, there is actually energy in that rotation, which will affect its overall energy at the end. So here what we just derived was the rotational kinetic energy for any object that has a moment of inertia and is rotating at some angular speed. So moving down below, we did A through D in class, but I will redo this if you need a refresher. So starting at point A, well, actually, let's read the whole problem. It says, a solid sphere has some radius and some mass, R1 and M1, is placed on top of a ramp with a height h and is released at time equals 0. The ball rolls down the ramp without slipping. We're going to first derive an expression for the amount of energy in the beginning. So we're looking at our initial energy, which is gravitational potential energy, which we know we can substitute as mgh. So our initial energy in the beginning is going to be m1, g, and h. That is how much energy is stored up in the very beginning. Okay, so the second part, the moment of inertia for the solid sphere is 2/5 mr squared. This is the moment of inertia for this object up here, for this solid sphere. For this solid sphere has this moment of inertia. This is only for solid spheres. You don't need to memorize this, but it's the idea that it does change depending on what type of object you have. Drive an equation for the amount of energy the ball will have down the ramp, expressed using terms of m1, r1, and v1. So what we're talking about is what type of energy will the ball have down at the bottom, and we want to express it using all this stuff. So at the very bottom, it's going to have actually two forms of kinetic energy. It's going to have our linear kinetic energy and our rotational kinetic energy. So there is, this whole object is moving down the ramp this way, and then it's also rotating, so you have energy there. The first kinetic energy, the linear kinetic energy, is pretty simple. We are familiar with that. That's just 1/2 mv squared. And the second one is going to be 1/2 I omega squared, what we got from what we derived up top. Now, the thing is, we know what our I is, and we need to get in terms of V, and so not using omega. We do know that omega is our linear speed over radius. We derived that in class earlier. So I'm just going to substitute this in, or actually I'm going to substitute this in for omega, and I'm going to substitute this moment of inertia for our I, which will hopefully give us all the terms that we are looking for. Plus 1/2, 2/5 mr squared, and then this is where it gets messy, v squared over r squared. Okay, so right now I'm looking at everything. We can simplify some things. Let's get rid of those 2's. Let's get rid of those r squareds. This is a v squared. So I'm left with this. Let's simplify and pull all the things out that we can. So our total energy at the bottom is going to be, let's just kind of write out what we have so far. 1/2 mv squared plus 1 square root, or not square root, parentheses m 1/5 m. That is an ugly m. I didn't make it any better, but that's okay. V squared. So if I look at this, I can see that I have mv squared times 1/2 plus 1/5. If I want to simplify that more, that's 5/10. That's 2/10, and that makes 7/10. So this whole thing, I have a 7/10 mv squared. So this is how much energy it's going to have at the very bottom of the ramp. And that leads wonderfully into C. So in C, it says find an expression for the linear speed of the ball will have at the bottom of the ramp express using all of this stuff. Basically, we're going to use the energy that we had in the beginning, which is M1, G, and H. We have the energy at the end, which is 7/10 mv squared. And that should be M1. And so if I equal those together, because of the conservation of energy, energy before equals energy after, then I know that I've got M1GH is equal to 7/10 M1V squared. So now I just need to solve for V. So I'm going to get V by itself. Basically, I'm going to multiply by 10/7 and divide by M1. I know the masses cancel. So V squared should equal 10/7 GH. And then if we make this all pretty, V is square root of 10/7 GH. Okay. Whoa. So we have a speed for an object, for a solid sphere that starts up at some ramp, at some height, rolls all the way down at the very bottom, it's going to have this speed. Woo. Now, why do we care about this? We care about this because of the problems down below. So if we go down, now it's looking at, well, what if we change it? What if we didn't have a solid sphere? What if we now have a cylinder? Now, instead of a sphere, it is just this soup can that, oh, it doesn't like that. What if I just had this soup can that was rolling through the center down the ramp? The only thing that changes is that the moment of inertia changes, which is now 1/2 mr squared. So do you expect the cylinder to have more, less, or the same amount of velocity compared to the sphere when it reaches the bottom of the ramp? Explain your reasoning. Well, if we think about it, you have 1/2 mr squared. That is the new moment of inertia, and the old moment of inertia was 2/5 mr squared. So that was the old one. I'm going to call that I1. We'll call this I2. So what is happening is that the moment of inertia is getting bigger. The moment of inertia is getting bigger. If the moment of inertia is getting bigger, then that must mean that our rotational kinetic energy is getting bigger. If our rotational kinetic energy is getting bigger, then our linear kinetic energy has to go down, has to get smaller. We still have the exact same initial energy in the beginning because it's still the same mass and the same height. So the energy in the beginning is the same. The energy at the end is still the same. But the idea is that you have now more rotational kinetic energy at the bottom because your moment of inertia is bigger. Because your moment of inertia is bigger, going from 2/5 to 1/2 mr squared. If your rotational kinetic energy is bigger, then your linear kinetic energy is smaller, which means that your velocity should be smaller than our solid sphere. So part E is, well, check it. See if that's actually true. Okay, well, we know that our initial energy is still M1GH. That does not change. What does change, though, is 1/2 mv squared. That is our linear kinetic energy. And this is, so I'll just put that down there. And our rotational, well, that's ugly, is now going to be 1/2. Our I now is going to be 1/2 mr squared. And then you still have omega squared. So this is the same thing as 1/2 I omega squared, and that's just broken up down below. Okay. So it's the same game as before. Now we just need to get things in terms of VR and H and all of that good stuff. We know from above, I can change this into 1/2 mr squared, and that's v squared over r squared. Again, remember, I'm getting this, where this comes from is just the idea that we had omega, and that's the same thing as v over r. And if you're squaring this, then you're squaring everything here. Okay, so your r's go away. And now it is just solving for v. We know that this is all, we can, okay, 1/2 mv squared, 1/2, so that's 1/4 mv squared. So we can just simply pull out, so our final energy is going to be v squared times 1/2 mv plus 1/4 m. And then we can do math. 2 over 4. So then this is just v squared is 3/4 m. Okay, so I know this is a lot of math, but what we just found is this is the ending energy in terms of v and m. We don't have to worry about r because that canceled out. But this is the final amount of energy we would have for a solid cylinder with this moment of inertia up here. If we compare that to our initial energy, v squared 3/4 m, and then solve for v, we then get v is equal to the square root of, again, masses can cancel out, and now I get 4/3 GH. And so if we quickly take a peek up above, this should definitely be lower than this, and square root of 4/3 is less than the square root of 10 over 7. And yeah, do notice that it's not a big change, but there is a change that even if you have the same radius and same mass, just having a different shaped object rotating will get you a different speed down the ramp, because again, it's the idea that energy is lost to the rotating part of it actually sliding upside down. Sliding upside down, actually rotating down the ramp. Okay. Now, the final spot is now replace the cylinder with a box, and suppose the box slides down the ramp without friction. So we don't care about friction in this spot. Assume that the box has the same mass as the cylinder and sphere. Do you expect the box to have more, less, or the same amount of velocity compared to the cylinder when it reaches the bottom of the ramp? Explain your reasoning. Okay, so here's the idea. The whole thing that we've been playing around with, yes, conservation of energy, is at the bottom of the ramp. If you have rotating objects, you have two different energies. You have kinetic energy that's just moving in a straight line, and you have the rotating kinetic energy. If you have a box without friction, you no longer have rotational kinetic energy. The box isn't rotating, and so it's only moving with a certain speed. Or only moving with linear kinetic energy. It's only moving in a straight line. If that's the case, then you have no energy lost to rotating, so the box should actually have not only more kinetic energy, linear kinetic energy, but it should also have more velocity. And that's where G comes into play of, yeah, does this, how does this relate mathematically? Okay, so now, again, M1GH, that's our starting energy. At the end, the only energy we have is the kinetic energy. The linear kinetic energy will be 1/2 mv squared. All right, so then if I do the good old conservation of energy equation and solve for v, 1/2 mv squared, again, masses cancel out. So then V is equal to 2GH all square root. And this is definitely greater than the square root of 10 over 7 GH, and also greater than square root, just double check, I'm going to run out of room. I'll do it down here, is also greater than 4/3 GH. Okay, so again, just wrapping this all up at the very end, is looking at the idea that rotating objects have energy. When they rotate, they have some angular speed, and if you have some angular speed, then that means you have some rotational kinetic energy. The more moment of inertia you have, that means you would have more rotational kinetic energy, and if you have more rotational kinetic energy, that means you have less linear kinetic energy. Thanks for watching. If you have any questions, feel free to email me. How's that?